I'm Aditya, and it is my pleasure today to talk to you about the paper titled FakeGuard, Exploring Haptic Response to Mitigate Vulnerability in Commercial Fingerprint Anti-Spoofing. This work is a joint effort between University at Buffalo and Zhejiang University. So over the last decade, fingerprint technology has become an essential component in user security, and it has diversified in its applications from government institutions to everyday devices, such as the laptops and smartphones. As the technology develops into different types, such as the optical, capacitive, and the recently introduced ultrasonic or in-display sensing, it has been able to provide a user-friendly experience and accurate authentication. It has the fingerprint remains still a dominant in the biometrics market, despite the introduction of several new technologies such as the voice or the face, and it is projected to grow even more in the future. So as the technology grows, attackers also develop new ways to steal the intellectual property of the users, which is stored behind the smart devices or physical locations protected by the fingerprint sensors. Since the fingerprint technology uses the fingerprint present on the human fingertip for authentication, the main goal of the attacker is to make sure that their fake replica of the fingerprint or the fingertip is as close as possible to the live finger. In the past, we have seen that even a photocopy of the fingerprint was even able to spoof the system, but recently attackers have also upgraded their gears, right? And they are using 3D printers to create really close replicas. And these are able to spoof even the advanced fingerprint technology that is present to date. So looking at the threat to the fingerprint technology, researchers in the security community has also developed several modifications to the software and hardware level of the current systems to provide a better anti-spoofing experience. However, many of these studies have three particular limitations. First, some of these studies assume that the fake finger created by the attacker would have some sort of a manufacturing defect during the fabrication process, and their software technologies would be able to detect it and tell it apart from the live finger. However, that is not always the case. The second is that many of these spoof studies may perform better on some of the materials, such as a fake finger created from wax or gelatin, but they might have not good performance on some other materials. So in a space where we don't know what material the attacker will use to create the fake finger, this is a huge limitation. Furthermore, many of these solutions have completely different hardware components than the current technologies already adopted in our devices. If the components are very different, then it becomes a hard challenge to make it adoptable in the current systems, thereby reducing its practicality. However, seeing that a fingerprint is a historic topic and there has been plethora of research done on it, it can be assumed that fingerprint security is good enough or it is resilient enough, and thereby it is not maybe a topic of concern to a lot of people. However, in our favor, we first try to highlight the security issues that are present in the current fingerprint. So we took 4 commercial fingerprint technologies being present in the everyday devices, such as the smartphone, laptop, access systems, and the smart locks, right? And each of these devices has a fingerprint system, which also has additional layer of anti-spoofing security, from 2D texture matching to a 3D anti-spoofing. Even beside having these anti-spoofing solutions, we were still able to spoof this system using a very high-resolution fake fingerprint, as shown in the image. We observed a spoof rate from 50 to 90%, which gives you the gravity of the situation. Considering that most of the people still use fingerprint, and it is present in millions of devices, and many of these attacks are still unreported, it is important for us to continue to advance the fingerprint security and make it more secure. So a human fingertip does not really only comprises of the fingertip, right? But it also has a complex biological network present beneath the fingertip. Now, many of the anti-spoofing solutions that are currently present only looks at the surface level information for for providing the additional layer of security. This is because whenever we talk about 3D technology, we can imagine like there is going to be an increase in cost. Currently, technologies such as OCT or photoacoustics can increase the cost of your sensors from a few dollars to over $500, thus limiting its practicality to everyday smart devices. So in this paper, we try to envision a new anti-spoofing solution which will be cost-effective, but should be able to give us a complete view of the fingertip along with the fingerprint, and thereby increase the security of the system. So polymers exhibiting viscoelasticity and weak intermolecular forces have been recently gained quite an attraction in the robotics and human-computer interaction community to measure the physical characteristics of interacting medium, such as its hardness, elasticity, and so on. We imagine that if a human fingertip presses on these elastomer surfaces rather than a fixed surface, then a deformation is typically going to occur, and this deformation magnitude will depend on the anatomy of the human fingertip. The deformation is generally governed by a partial differential equation system, which typically comprises of stress tensors, strain tensors of both the fingertip and the gel surface. Our hypothesis from this was that considering a human fingertip is a more complex structure as a multi-layer, and this is like very different from a fake finger, which is typically a single layer structure, this response that we can get from the medium interacting with the surface is going to be much different between these two live and fake finger. Our proof of concept tries to show the different responses we get between a live finger and versus a spoof material. Observing these scenarios, we tried to create a system called FakeGuard, which is a first haptic-based anti-spoofing platform. As similar to the traditional technologies, we asked the users to naturally press on the fingerprint sensor, and we record a sequences of images. These images are later processed and analyzed to detect whether the input comes from a live or a fake finger. Compared to the previous technologies, our study offers 4 important advantages. First is the liveness. In our study, we make no assumption about the fake finger or what material it was used to create it. We also make sure that our response that we are trying to capture cannot be remotely acquired by an attacker using a spyware technology. The hardware design tries to make sure that our cost of our entire sensor is below $35, increasing its user acceptance and practicality. Lastly, we need to make sure that the sensor is able to accommodate the user all throughout the user demographics and in different environmental conditions. So let's first look at the hardware. So the hardware of the FakeGuard facilitates the optical perception of both the haptic response and the fingerprint textures. It is the main component of this hardware is the sensing surface, which is a dual-layer PDMS gel. We use PDMS gel because of its rheological properties and its sensitivity to the human finger. This hardware is supported by components that you typically observe in the optical sensors, such as the LEDs for providing lighting illumination, acrylic film to make sure the surface is not reflective, off-the-shelf cameras for capturing the images, and a Raspberry Pi for the computing resource. Now, what we do is we ask the users to naturally press their fingertip on our sensing surface, which is the PDMS gel, while our camera will be able to record a sequence of 2D images. We later use a photometric stereo algorithm to convert the sequence of 2D images into a 3D image to later do the feature extraction. As you can see from our image shown in the top right corner, the images we capture are very detailed, and they are significantly different between the live and the fake finger. Now, we know that a lot of the technologies that are already existing in the market on the fingerprint also has a software mechanism attached to it. That mechanism typically extracts the level 1 and level 2 fingerprint textures to provide the classification. So it is important to make sure that our technology is not just like compatible on the hardware side, but also on the software side, where we can use these existing algorithms and directly apply to the images that we are capturing in our system to extract the given features. So in this slide, we follow the same step that a traditional fingerprint researcher follows, such as taking the images, pre-processing it using the histogram equalization and normalization, separating it from the background and using the level 1 and level 2 feature extraction. As you can see from the image, our response supports the acquisition of these textures that are highly usable for user authentication. Besides the fingerprint features, we also consider the spatial distribution of the fingerprint, and we extract the first order and second order statistical analysis of the neighborhood pixels. These statistical analysis will be able to give us the deformation that can occur in the during the interaction with the gel surface. And we use these features along with our fingerprint for our classification. Since this work is a first exploratory study, we try to analyze it using different classifiers such as the logistic regression, SVM, XGBoost, KNN, and CNN. So before we talk about the results, let me go over the experimental procedure. So in our study, we recruited 20 subjects, and we asked each of the subjects to first present their live finger towards our sensor while we record the images. Then we created different fake fingers of the subjects using their index, middle, and thumb fingers. Some of these fake fingers can be seen in the slide over here, and these are highly detailed resolution fake fingerprints. Now, we also make these fingers not just from one material, but in our study, we use 8 different materials to make sure we do a comprehensive analysis. Another thing we note into consideration is that while we select these fake fingers, we do not select all the fingers that we are fabricating, but instead we make sure that these fake fingers in our study are able to spoof one of the 4 commercial devices in our attacks and have high spoofing performance, thereby having no bias in our study and making our results look realistic. For the metrics, we use the denial rate and the spoof rate, which is the most common metrics used in the fingerprint security. And let's talk about the performance evaluation. So the first evaluation we do is the supervised scenario, where the classifier is trained on multiple users and used to identify a specific target. We notice that even as simplified linear boundary classifiers are able to achieve a very low classification errors. And obviously, if we use stronger classifiers like CNN, we are still able to maintain that good accuracy. Our performance is good on majority of the subjects. The few lower performance we observed was mostly due to the inaccurate sensing process, where a user, rather than pressing, slided his finger on our sensor. But despite the supervised scenario, the main important thing we need to consider is the unsupervised scenario, where we would not know what material the attacker will use to create the fake finger and be able to interact with our system. Now, many of the studies that are conducted in the past in this topic do not present much results in the unsupervised scenarios. Thereby, it is not really practical to evaluate its security. So in our study, we trained the classifier on only the live fingers, and then we asked it to detect whether the new sample that has been presented comes from a fake finger or not. So our classifier will generally assign a probability to a live finger to a new sample being as close as possible to the live finger or not. If we have a threshold being set on this probability, we can see that we can still maintain a spoof rate as low as 2.43%, despite our classifier having no knowledge of the fake fingerprint. This comes from the fact that our feature set is highly distinct between the live and the fake finger, and we are able to provide better spoofing performance. We also want to make sure that our spoof study is as comprehensive as possible, and we took in many spoofing materials in our study. And as you can see from these graphs, that despite the materials, we are not seeing any patterns towards having a weakness towards a particular material across the subjects. This just means that our technology is really adoptable across the devices, across the materials. Lastly, we do identify some of the regions where we can further improve our system, such as we observed a lower performance when it comes to someone applying a hard pressure or during high temperatures. However, many of these attacks that are presented here really can have overlasting damage to the sensor, and these attacks thus would not be as hidden and can be easily detected towards the forensics. Now, improvement in the PDMS gel is a very active topic in the research community, and we are continuing to explore further to optimize our sensor. So to conclude, in this paper, we try to expose the limited security of the current commercial fingerprint devices, and really highlight the need for better security. We produce a new system called FakeGuard, which uses the haptic response to increase the anti-spoofing experience, and we validated its result across several different materials. Now, our FakeGuard is compatible on both the optical with the optical fingerprint sensors on both the hardware and the software level, and we continue to make improvements towards it. Thank you for listening.